I'm going to share my screen with you. What I'm planning to do today is, for this session, is actually do one final example of a rectangular frame where we have actually columns on both the columns and the beams, because I don't think we have done any example like that. So I wanted to finish this hour with this example, and then next week we start afresh with a completely new topic. Okay, so so it's a tutorial question that we are covering now, consisting of a rectangular frame with horizontal loads and with horizontal loads on the columns. Okay, just to show you the kind of extra collapse mechanisms that you get. Okay, so I'm going to start the presentation mode to make it easy. Okay. Yeah, if you have any questions, please, at any stage, just stop me and ask the question. Okay. So what we're planning, the plan for today, or the learning outcomes, will be, first of all, to carry out the analysis for a rectangular frame, and the frame has got loading applied onto the columns. So we have some horizontal loading applied to the columns. And then we're going to determine the critical mechanisms from that, for that frame, and then draw the bending moment diagram for it. Okay. The rules are the same, so there is nothing new here. This is exactly what we have been using in the past, so that's okay. This is the frame. Okay. So what we have an asymmetrical rectangular frame, right? Where we have a vertical load applied here at D, lambda V20. Lambda V, this is the load factor for the vertical load. Okay. And then we have a horizontal load, lambda H15. That means 15 times lambda H, and lambda H is the load factor for the horizontal loading, which is the same at the other side. They don't have to be the same, but in this particular example, we've got the same lambda used on both sides of the columns, CA and EG. Okay, given the load factors are given here. So for the horizontal load, the load factor is 1.4, and for the vertical loading, the vertical load factor is 1.7. In other words, what you need to do here, you need, for the vertical load, you need to multiply here the 20 by 1.7, okay? And that will give you the load, the vertical load in kilonewtons. And similarly, you take the 15 here and the 15 at the other end, and you multiply them by 1.4, which gives you the horizontal loading on AC and EG in kilonewtons, okay? Which is what I'm going to do on the next slide. All the dimensions are given here. The frame is 8 meters in the horizontal direction. The load at D is applied in the middle. So we have 4 meters, 4 meters. And then column AC is 3 meters long, and the load is applied in the middle. And column EG is 6 meters high, with the load applied in the middle in this direction. Okay. So this is the problem that we have. And the question is to determine all the collapse mechanisms, all the possible collapse mechanisms, and then draw the bending moment diagram for the critical mechanism. All right. So first of all, how many, can anyone shout how many, what is M for this column, for this, sorry, for this frame? Do you agree we have a hinge at B, C, D, E, and F? Okay, so we have 1, 2, 3, 4, 5. So M is 5, so we have 5 possible hinges. okay? We have two unknowns at A and two unknowns at G. So we have 4 reactions. 4 minus 3 equations of equilibrium equals to 1. So n, little n is equal to 1. That's the degree of redundancy, okay? So the degree of redundancy for this frame is 1. And then you do the difference, m minus n, which is 5 minus 1, 4. So we have 4 independent mechanisms for this frame. And n plus 1, which is 1 plus 1, 2. We only need two plastic hinges for total collapse. Now, what are the independent mechanisms? We said there are 4 independent mechanisms. Obviously, we have the beam mechanism for AC, we have beam mechanism for CE, we have beam mechanism for EG, and obviously we have sway of the frame. That's another independent mechanism, and these are the 4 independent mechanisms, okay? So I've got them here. M is 5 possible hinges, N is 1 degree of redundancy, 4 independent mechanisms, and n plus 1, 2 hinges needed for complete or total collapse, okay? Anything not clear, please just stop, okay? Stop me. So let's start with the first one here. So we are going to start with this beam mechanism, okay? You can turn it around if you want. It's a column, but if you turn it around if you want, if that helps you, you can do that, okay? So this is the, this is actually this one. I started with this one, sorry. I started with this one, CE, all right? You can start anywhere, but I've started with CE. So we're looking now at the beam mechanism of CE. This is the beam, CE, and the load, when you multiply 20 by 1.7, it gives you 34 kilonewtons. So the vertical load is 34 kilonewtons. We have hinges forming at B, C, and E, right? Remember, in this particular case, MP is the same everywhere, okay? If you get different values of MP, obviously, you need to be careful that the hinge will form in the weaker member, as usual, okay? But in this particular case, because we have MP is the same for the columns and the beam, then obviously the hinge will form at the location of the corners in here, okay? So this is the beam mechanism, right? And then by symmetry, because the 34 is applied in the middle, so we have symmetry, and therefore if the angle is theta at this end, we have theta at the other end, and obviously we have theta and theta in the middle at C. So when we write the external work and the internal work, the external work is 34 times the displacement, this displacement here, the vertical displacement, which is 4 theta, because remember this distance is 4, okay? So we have 4 theta is the displacement. So 34 times 4 theta equals, we have MP theta at C, at B, we have MP theta and MP theta at joint C, and finally we have MP theta at joint E here. So that gives 4 MP theta, 1, 2, 3, 4 MP theta. So therefore, theta and theta will cancel. So, and 34 times 4, okay, divided by 4 will give you MP. Okay, I repeat, MP will be 34 times 4 divided by 4, which gives 34 kilonewtons meters. So the first mechanism, the BE mechanism, gives MP 34 kilonewton meters. Okay, so that's the first mechanism. Now we're going to look at the next mechanism, which will be AC, and then we do EG. Okay, so beam AC, effectively this is the column AC, and this is what we have. Okay, remember that the column at the base here is pinned. Okay, the column is pinned, so therefore there is no hinge at A here. There is no hinge at A. Okay, there's no hinge at A. We have a hinge obviously forming in the middle here, and we have a hinge forming in the corner at C here. Okay, so therefore we have if the angle is at A is theta, then the angle at C here will be theta by symmetry, and therefore we have theta and theta, and these are the moments at the location of the hinges with the correct directions shown. Okay, now the load here, this is if you go back, it's 15 times 1.4. Okay, 15 times 1.4, which gives you 21. Which gives 21. Now the external work will be 21 times the displacement. This displacement here, and the displacement is 1.5 theta, because the height of the column is 3 meters. The height of the column is 3 meters. So this distance here is 1.5 meters. So therefore the displacement, this displacement is 1.5 theta. Okay, so we have 21 times 1.5 theta equals, we have mp theta plus mp theta plus mp theta, that's 3 mp theta. Okay, then you simplify the theta from both sides, and then mp will be 21 times 1.5 divided by 3, which gives 10.5 kilonewtons meters. So the second mechanism, the beam AC mechanism, gives mp equals 10.5 kilonewton meters. Now we're going to do the same this time for this column here, EG, and we have the mechanism of the beam mechanism of EG. So let's do it. And you can see that the load is the same. 15 times 1.4 is 21 kilonewtons. And remember, G is pinned here. So we have a pin. There is no plastic hinge forming at G. Okay, you only get a plastic hinge if this is fixed, fully fixed. Okay, but it's because it's simply supported. So therefore, there is no hinge forming at G. We have a hinge forming at F, and we have a hinge forming at E. So let's do that. So this is beam EG mechanism, and this is what we have. The load is 21. The height of the column is 6 meters here. So this length from the midpoint, the bottom is 3 meters. So therefore, we have 3 theta is the displacement. So this displacement is 3, okay, 3, that length times theta. And then we have got the hinges at these 2 points here, and no hinge at E. So writing the equations of external and internal works, we have 21 times 3 theta. Okay, 21 times 3 theta. That's the external work. And then the internal work, we have mp theta, and mp theta, 3 mp theta, which gives, when you simplify the theta, so we have 21 times 3 divided by 3, which gives 21 kilonewton meters. So this is the third mechanism, which is the beam mechanism. The next one, beam EG mechanism. So the next one, we said there are 4 independent mechanisms. So the next one is the sway of the frame. So now we're going to look at the frame as a whole, and then we're looking at the mechanism of the sway of the frame, which is the next sway, which is the next mechanism. And this is the frame here, okay? This is the frame, and this is how it's going to sway, right? We have the vertical load, obviously, and we have the 2 horizontal loads, and the horizontal and the sway mechanism, which is a horizontal movement, is actually caused by the 2 horizontal forces here on each of the columns. Remember, there are no hinges forming at the supports because they are simply supported. Okay, it's not fixed. They are not fixed. So we only have a hinge at this column here at the corner, and we have another hinge forming at this corner here, okay? And remember what we said? We said we only need two mechanisms, we only need two hinges for total collapse, isn't it? Okay, that's what we said earlier, right? If you go back here, although we have 5 possible hinges, okay, although we have 5 possible hinges, we actually need only 2 for total collapse. So therefore, the sway mechanism, where is it? The sway mechanism is a mechanism of total collapse, okay? Now, I forgot to mention that if you go back here to the to this mechanism, the beam CE mechanism, we have 3 hinges, which is more than the 2 we need for total collapse. And therefore, what you can say here is that this beam CE mechanism is actually an over collapse mechanism. It's an over collapse mechanism. Why? Because we've got more hinges than we actually need for total collapse. Okay. So this is the sway mechanism. Yes.
Hello, sir.
Yeah.
What did you call it? This CE or something? Okay. Yeah. What did you call it?
Okay. The number of hinges, n plus 1 here, 2 hinges. We only need 2 hinges to cause total collapse. Okay. We only need 2.
Yes.
Although there are 5 possible hinges, but we actually only need 2 only for total collapse. Okay. And therefore, any number higher than this, that means you have got an over collapse situation. In other words, you have got more hinges than you need. Now, if you look at this beam here, okay, if you look at this beam CE, it has got 3 hinges at C, D, and E. In fact, if only a hinge form at C and a hinge form at E, the whole thing will collapse, because as soon as a hinge form at C, you can see what's going to happen here, because that's not fixed. This is a simple support. So when you have a hinge forming at C here, that part will just collapse, and that part will just collapse. So the whole thing, as soon as C and E have got hinges, the whole frame will just collapse, even without the hinge forming at D.
Okay.
That's why. Okay. So that's why for this hinge, for this one here, we don't actually need all 3. These 2 will be sufficient for the whole frame to actually collapse. Okay. So this is effectively an over collapse mechanism. All right. Okay. Sometimes you do get it in some of the examples like this one here. Okay. Where you have got actually more hinges than actually you need. Is that okay?
Yes, sir.
Okay. Okay, so going back now to the sway mechanism. So now we can write the external work. Sorry, here, the displacement is the same as this. We have a simple horizontal movement. So the displacement at the top of this column and the displacement at the top of this column are equal, obviously, because we have a simple sway movement. So therefore, by compatibility, we have 3 theta is equal to 6 gamma, okay? Because the column height here, the height of this column is 3 meters. The height of this column is 6 meters. So you have this displacement is 3 theta, and this displacement here is 6 beta. So when you put 3 theta equal to 6 beta, it gives you the relationship between theta and beta as this. So you have theta effectively is equal to twice theta, okay? Now we can write the external work. So the external work, we have 21 times the displacement. Please be careful here. It's always the displacement at the level where the load is applied, not at the this one. This is here. This is actually 21 times the corresponding displacement at the load level. So basically, it's half of 3 theta, okay? Because this displacement here is half of 3 theta. And similarly, for this one here, for this load, it's 21 times this displacement, which is half of 6 theta. And this is what we have here. So we have 21 times 1.5 theta, okay, plus 21 times 3 theta, which is 3 beta, which is half of this, 3 beta, equals we have MP theta at this end, at this hinge, and then we have MP beta at this hinge. There are no hinges at the supports, so that's it. So we have MP theta and MP beta. Now you can simplify by substituting, either you substitute theta by 2 beta, or if you want to substitute beta by theta over 2, and when you simplify, you get exactly the same answer. Okay, you get exactly the same answer. What I've done here, I've substituted this theta by 2 beta. So 1.5 times 2 is 3 beta. So now the beta everywhere, we have 21 times 3 plus 21 times 3 equals MP times 2 plus MP. And then when you simplify and together, when you regroup and simplify, you get 126 equals 3 MP. So MP is 126 over 3, which is 42. So we have MP is 42 kilonewton meters from this sway mechanism. So these are the 4 mechanisms, the 3 beam mechanisms plus the sway mechanism, okay? And we haven't finished, because now we need to start looking at the combined mechanisms. And we are going to combine some of these mechanisms for analysis. Is it clear up to this point for the independent mechanisms? I think it's very simple. If you have any questions, please ask, okay? Before I move on to the next slide, and I'm going to start looking at the combination of mechanisms. The first obvious mechanism, obviously, is to combine the sway and the beam mechanism. So that's one possibility. So let's look at them one by one. So this is this is the sway, okay? This is the sway here. When we combine it with beam CE, this beam. So I will go back again one step, if you want. So I'm taking this mechanism here, and I'm going to combine it. Look at it well. See how this beam is rotating, okay? Now I'm going to combine it with this here, okay? So I'm combining these two together, which gives me, when you combine them, it gives me this one. Remember what we did, what we said before, that because this column rotates in the clockwise direction and this beam rotates in the clockwise direction as well, then obviously the hinge at B, the hinge here, at C, the hinge at C here will cancel. So that hinge has disappeared, it's cancelled because the column and this beam here rotate in the same direction. And we only have a hinge at D and the hinge at E. All right. So what you can say, what you can see here is that now we have got 2 hinges only. You see, for this mechanism, we only have 2 hinges, which is exactly what we need for total collapse. So this is a total collapse mechanism situation, right? And we have the vertical load and we have the horizontal loads as shown. Now, if we start on the left side and the angle at A is theta and the angle at the other side is beta, then we have displacement 3 theta equals to 6 theta, okay? Whereby, for compatibility, we have the same displacement at the top here. So therefore, that gives you theta equals to beta, or beta is theta over 2, okay? Then we have a hinge, as I said, at this location here. So we have MP theta and MP theta. I'm sorry here, yes. And then at this hinge, we have MP theta, MP theta and MP beta, right? So now we can write the equations of for the external work and the internal work. Okay, for the external work, I'm going to go through it very, very slowly. Please follow with me. So we have 21 times the displacement here, which is half of 3 theta. all right? Plus, we have 21 times this displacement, which is half of 6 theta. So that's 3 beta here. Sorry, half of 6 beta. So that's 3 beta, okay? Plus, we have 34 times this displacement. And this displacement is equal to 4 times theta. 4, because the length, this length here, this length is 4. So it's 4 times theta, right? 34 times 4 theta. Then equals internal work, we have MP theta plus MP theta. This is for this hinge. And then for this hinge, we have MP theta and MP beta, okay? Which gives me 1, 2, 3 MP theta, okay? Plus MP beta. And then what I've done here, I've substituted theta by 2 beta. So now I've got everything here substituted as a function of beta, which allows me then to calculate the summation here, okay? The summation here, and then simplify by beta from both sides of the equation, which gives me 398 equals 7 MP, which means that MP is 398 divided by 7, which gives 56.86. So 56.86 kilonewton meters for the combined mechanism of CE and the sway mechanism together. Is that okay for this mechanism? Clear? I just want to check. Okay, so yes, so that's the for this mechanism. Okay, so that's for this mechanism. We've got 86. Now, what we're going to do now? We have another. You see, as a rule of thumb, remember this, please. Remember this rule. As a rule of thumb, when you consider the combination of mechanisms, there is no point in considering mechanisms that do not cancel any hinges. In other words, any combinations that will cancel hinges is a good one. Why? Because it gives you something critical, okay? But because any extra hinges doesn't give you a critical situation. An overcollapse is not a good thing. It doesn't give you a critical solution. So why I'm saying this, the reason I'm saying this, because now I need to look at the other possible combinations. Okay, what are the other possible combinations that I can consider? Here, remember, we have looked at the sway mechanism with the beam, with this beam mechanism together. So we have combined the beam mechanism with the sway. Now I have the other possibilities. The other possibilities I can combine with this beam mechanism, or I can combine with this beam mechanism. If you combine with this beam mechanism here, if I combine with this beam mechanism, do you think what's going to happen with for the hinge at this joint here? Do you think it will cancel, or there will be a hinge?
Hello, sir.
Yes.
Yeah, this sway mechanism, what load is causing it? What load is responsible for this sway mechanism?
Are you talking about this combined here, this combined mechanism?
No, not the combined. The sway mechanism independent.
You talk about this one?
Yes.
Yeah, it's the two loads here. The horizontal loads on each column. These two horizontal loads, they are the ones causing collapse, causing the sway mechanism. Okay, and that's why you can see we have included them here, both of them. Okay, because it's a sway, so it's a horizontal movement, and therefore it's caused by these two forces on the columns. Okay, and for the combined mechanism, it's all three forces causing this mechanism, because we are looking at the combination of the beam and the sway. So all forces here contribute to this mechanism. Okay? What I'm trying to do now, I'm trying to look at what other combinations I can consider. Now, if you go back here, see this beam mechanism here, okay, this one. You can see that this segment here is rotating in which direction, clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. Yes, this one is rotating which direction, clockwise or anti-clockwise?
That's clockwise.
Yeah. You see when you put these two together? Let me go to the actual mechanism. I just need to explain this on it. See here, if I combine this mechanism with this beam mechanism, okay, can you see that this member and this member here will come closer to each other? Do you agree with that?
Yes.
Because they are rotating in opposite directions. Okay, for this beam mechanism, this segment is rotating anti-clockwise, whereas this is rotating clockwise, as we said. So therefore, if I add the beam mechanism here, that will give me a hinge at this corner. All right? Okay, so that's not good. So I don't need to consider this combination. The other one is more interesting, because look here at this end. At this end, if I add the beam mechanism here, right? You know, this beam, let me go back again. Can you see here, for this beam mechanism, this segment is rotating in which direction? Clockwise. You agree? Yes? Okay, look here. Which direction this is rotating? This is rotating?
Anti-clockwise.
Anti-clockwise. Good. How about this one?
Anti-clockwise.
See? So these two here, this member and this member, are rotating in the same direction. Correct?
Yeah.
Yeah, they are rotating in the same direction, anti-clockwise. So therefore, when I take this, sorry, not this one. When I combine this mechanism with the beam mechanism here, this hinge will actually cancel, because this member here and the beam mechanism for this member here will be rotating in the same direction, and therefore, when I combine them, I get this hinge cancelled. So what I've done, I repeat again, what I've done here, I've taken this mechanism here, which is already a combination of CE and sway. I've taken this mechanism and I've combined with it the beam mechanism for this part here, for this one, okay? And when you do that and you put them up together, this is what you get, okay? Now we have a hinge at this point here in the middle, and we have the hinge there. All right, and the hinge at this corner has cancelled, because this member and this member here are rotating in the same direction. Okay, so this mechanism that you see is actually the combination of the combined mechanism that we have seen, which is CE and the sway, plus the beam mechanism for this column here. right? And thus, so we have a new.
Sorry, sir.
Yes.
So here you are combining three mechanisms.
Yes, exactly. So what we've done, we have combining this mechanism here, which is beam and sway. So I'm taking this mechanism and combine with it a beam, this beam mechanism. This hinge will disappear because the two members, these two members are rotating in the same direction. But now I have a hinge, obviously at where the 34 is applied, and I have a hinge where the 21 is applied. And I have exactly two hinges, which is exactly what I need for total collapse. And there is no extra, there is no over collapse or anything. Okay, and that's the combination. As I said, as I explained earlier, the combination with this beam mechanism will give me a hinge here, which I don't want. Okay, we don't need it because it will give me more hinges than I need, and therefore that will not be a critical mechanism. This is potentially a critical mechanism that we need to analyze. Okay, is that clear? So now we have got the that's the mechanism. If you start now, in order to if you start at this end and the angle is theta, you can actually find this one here. I've done it with this geometry. You can see with all these dotted lines. You don't have to do it like this. You can use the principle of superposition by adding all the angles together. So you've got this angle here and the angle from there. See what I mean? Because you got this beam mechanism, you've got this sway mechanism, and you've got the obviously the mechanism 5, which is this combination of these two. So if you want to use the principle of superposition, you get exactly the same angles as I have shown here. I leave it to you. Do it outside if you want, and check it for yourself. That you can use the principle of superposition to give you the angle there. Okay. Anyway, so this is what we have. Now we have theta there and theta here. Okay, because it's 90 degrees, so you got the same theta there and there. And then by symmetry, because the load here is applied in the middle, 34. So if we have theta at this end, we have theta at the other end. And then because the angle here is 90 degrees, because it's 90 degrees, so this angle here with the vertical line, this is the vertical line, you have theta and theta, okay? And then this is from the principle of superposition. This is the beta. The beta here is from the sway mechanism, and this is from the combined and the beam mechanism. So that gives me effectively, I have 2 beta plus theta here, 2 beta plus theta. And then this angle theta, you have theta on this side, you have also theta on this side because you have parallel lines, okay? And then these are the moments. So we have MP at this joint, and then we have MP and MP for this joint here. And all we need to do now, because we know the angles, all we do now is write the external and internal works. Okay. So for the internal work, I start the external. I start from this side. We have 21 times this the displacement here, which is half of 3 theta. Okay, plus 21 times the displacement. This displacement here from there to there. So 21 times the displacement here, which is 3 times 2 theta plus beta, okay? 2 theta plus beta. So that's 21 here, because remember the column here is 6 meters high, okay? So the midpoint, we have 3 meters. So therefore the displacement is 3 times 2 theta plus beta, 2 theta plus beta, okay? So the displacement here, that displacement from the original, always from the original state position. So it's 3 times 2 beta plus theta plus 34 times the displacement, and this displacement is 4 times theta. 4 times 4 is this length here, 4 times theta, equals, we have mp theta plus mp theta plus mp theta plus mp 2 theta plus beta. I repeat, we have mp theta plus mp theta plus mp theta plus mp, this angle here, which is 2 theta plus 2 beta plus theta. So therefore we have 3 mp, 1, 2, 3 mp plus mp 2 theta plus beta. Now you can substitute everything by as a function of either as a function of theta or as a function of beta. It doesn't matter. I've done it here as a function of theta, okay, and then simplified the beta. So I have 587 equals 10 mp, which gives me 58.7. It gives mp 58.7 kilonewton meters. Okay, so as I said, you can use the principle of superposition here from the previous ones, and you get exactly the same angle here to beta plus theta. Okay, so this there are no other possible combinations that will give me a possible critical solution. I think we have covered all of them, the individual collapse mechanisms and the 2 possible combined mechanisms. So I'm going to summarize it here. Summary. So beam CE gives MP34. Beam AC mechanism 10.5. Beam EG mechanism gave us 21. Beam at the sway mechanism gave us 42. And the combined mechanism, which is combining beam CE and sway, gave us 56.86. And finally, a combined mechanism, which is combining 5 and the beam EG, gave us 58.7 kilonewton meters. Remember, these are not loads, these are moments, okay? So therefore, the most critical solution is for the maximum value here, and the maximum value, the most critical, is for MP 58.7. What is interesting really here to note is that if we did only the combined, if we did only the independent mechanisms and the combined and this one, we would have missed the actual solution, right? And that's why it's very important that you consider all the possible combinations that will that could give you a critical solution. And so therefore, in this case, we got up to the very last. We got up to the very last mechanism to actually find the critical solution. Okay. So yes.
Why is combination 6 the critical? I thought it's supposed to be the least.
The least for the loading.
Okay.
Okay. But for the moment, you are looking at the high at the because remember, this is the plastic moment.
Okay.
That's the plastic moment, and therefore, when you are looking at the structure, the highest moment will give that. That's the one that causes for the total collapse. For the collapse, okay. For the loading, okay, you are looking at the load at the first load that will give you collapse. That's your critical load. Okay, so remember this, please. Okay, if you are looking at the loading or the critical or the load factor lambda, you are looking at the minimum value, obviously. But if we're looking for the moments, you are looking at the because it's the plastic moment. So that's the moment that will give you the plastic collapse. Okay. Right. So what we need really is we need really to check because there is no guarantee. We need to check that this is actually the true solution, right? And in order for this to be the true solution, and there is no other possibility, all three conditions of equilibrium, mechanism, and yield must be satisfied. Okay. If you go back to this mechanism itself here, the equilibrium is satisfied because we said external work equals to the internal work. So that's equilibrium. So that's satisfied. We are running out of time, so because it's 10:02. Is that okay? I go over on by about 5 minutes. Is that okay? Okay. So the equilibrium is satisfied. The mechanism is satisfied because we've got two hinges, which is what we need for total collapse. Okay. So the only condition that must be checked is the yield condition here, this one. Okay. Because conditions, equilibrium and mechanism are already satisfied. So I need to check this one, right? Now, look at this mechanism here. Do you agree? What is the bending moment here at this point? At this support, what's the bending moment?
0.
Yeah, and there also 0, isn't it? And we know the moment at this hinge is MP. We know the moment at this hinge is MP. So the only two locations where we don't know what the moment is are these two locations here, C and E, isn't it? So we need to know what is the bending moment at this joint and what is the bending moment at this joint. We need to find the moment at these two joints and compare them with the critical MP in order to satisfy ourselves that the yield condition is satisfied. Okay, so I need to determine the moments at the unknown locations and compare them with this moment here, whether hopefully they will be less than 58.7, in which case the yield condition will be satisfied, and that will be this solution here, this mechanism, and this solution will be the true solution. Okay, so I'm going to show you a little bit quickly how you can actually solve this. Essentially, it's very simple. All you need is to take a number of cuts and do some equilibrium conditions, and then you find the moments. Okay, what I've done here, this is the mechanism itself, with showing all the moments. So we have MP and MP at D and F. We have 0 moment at A. We have 0 moment at G. And the only moments that we need to determine, sorry, I forgot this one as well. We need to determine the moment at B. We need to know the moment at C. And we need to know the moment at E. These moments at B, C, and E, we need to calculate them and check that they are actually less than or equal to MP. In order to find
the moment at B is MP.
No, look. Is there a hinge at B?
Okay.
Yeah, we only have hinges at these two. So I need to know the moment at B, at this location, Yeah. So therefore, I think what you could do, you could start by taking a cut at E, and then you can take a cut you could take a cut at D, for example. We give you two equations. Okay, there are a number of possibilities that you can solve this. There are a number of possibilities. There isn't only one way, but they all give you the same answer anyway. So what I've done in my case, I can give you slowly. What I've done, I've taken first the frame as a whole. I know that HA plus HG will be equal to 21 plus 21, which is 42. And then the horizontal reaction at A plus the horizontal reaction at G will give us 34. So that's two equations already. Okay, so that's horizontal equilibrium of the frame and vertical equilibrium of the frame. So I have two equations here. Then what I did, I then considered the equilibrium of member FG. Can you see here FG? I've taken FG, I've taken a cut. I've taken a cut at F, right? Why I've started at F? The reason I started at F, because I know the moment at F is MP, okay? So I have taken a cut at a location where I know what the bending moment is, which is MP here. So if we take the equilibrium of EG, okay, and you take moments about F, straight away, you get the horizontal reaction at G, 19.57 kilonewtons. And I've called this equation number 3. Then what I did, once I've got HD, I have moved to the equilibrium of subframe DEFG. So I've taken a cut there. Can you see? And the reason, again, I've taken a cut at D is because I know the moment at D is MP. We know it. So we know the moment at D is MP. So if I take a cut at D and I consider the equilibrium of this subframe, straight away I can determine FG, because HG we already know it. So straight away when I take a cut at D, it will give me VG, horizontal reaction at G, 28.8. Okay, so now so far I've got HG and I've got VG. When you have HG, you can substitute it here, it will give you HA. And when you have VG, you substitute VG here, it gives you VA, which is what I have done. So I've got HA 22.4 and I've got VA 5.27. These are the reactions at A, right? And to finish it off, what you could do, you could take the equilibrium of EFG here, okay? Because now we've got the reactions. That was the most difficult part, is to find these reactions. So we've got them now. If I take a cut at E, straight away I will get the moment at E, which is 54.42, and you can see it's less than MP, okay, which is 58 something, okay, 58.7. Then what I've done, I've taken the equilibrium of A, B, C, this one here. So when you take the moment a cut at C, we know HA, we know VA. So when you take a cut at C, straight away you get the moment at C as 35.7, which is less than MP. And finally, I'm going to take a cut at B, which is what I've done here. I've taken a cut at B. I know the reactions, so therefore I can determine MB 33.6 kilonewton meter, which is less than MP. So now we've determined the moment at E, the moment at C, and the moment at B. And the good news is that all 3 moments are actually less than MP, which is 58.7. And therefore the yield condition is satisfied, as well as the equilibrium and the mechanism conditions. So therefore this mechanism, okay, so therefore this mechanism is definitely the only and unique mechanism. There is no doubt about it, because that's the uniqueness theorem, okay? Yield condition is satisfied, equilibrium condition is satisfied, mechanism condition is satisfied. So therefore this mechanism here is definitely the true and only solution. And we have checked it to satisfy ourselves, okay? So therefore, now we've got all the moments. At A is 0, at B we've got the value here, at C we've got the value, at D we've got MP here, at E, at F we've got the values, and at G is 0. Remember, you always plot the bending moment diagram on the side of the member where there is tension. For example, at F, tension is on this side here, on the right. If you take E, for example, you have tension at the top. If you take D, for example, you have tension at the bottom here, etc. Okay, so you plot the.
Sorry, so how do you identify? How do you identify where there is tension?
Okay, look at F. Look at here. That's the direction of the moment. Okay.
Okay.
So this moment is going anti-clockwise. Is the tension is the member going to be in tension on this side, on the right, or is it going to be on the left? Take a ruler, if you have a ruler, and bend it with an anti-clockwise moment this way, and tell me, do you think the tension is on this side here on the right, or is it tension on the left side?
It should be on the right.
Exactly. So we've got tension on the right here, okay? And this is where you plot the moment on the right side, okay? All right, here at E, you've got tension at the top, so you plot the moment at the top here, 54, okay? At E on the column, you got tension on the right, so you got tension on, so you plot the moment on the right here, 54, and you can see that they are in equilibrium. And similarly, for C, we've got the tension at the bottom, and you got tension on the right here, okay? And at B, we have tension on the right and tension on the right here. So this is where the bending moment is plotted, okay? And then you join the points together, and this is the annotated bending moment diagram for the whole frame for the collapse mechanism. This is the bending moment diagram for the true collapse mechanism, okay? We have determined everything. The only thing, if you want to do it as an extra exercise, is to determine this point of contraflexure. I'm not asking you to do it. I think that's good enough. If you get to this stage where you have got all the moments have been determined, okay? And that's the bending moment diagram for the frame, right? And that completes this problem, okay? And I am sorry, I am a little bit about 10 minutes. It's 2 o'clock. Can I take any? Have you got any questions before we finish, please? Any questions? Okay, so I'm going to stop the recording. How do I stop the recording? So thank you very much, everyone. So stop it.